we go into the second topic, which is the sources, transport, and sinks of trace gases in the atmosphere. Trace means very minute amounts or very small amounts of gas in the atmosphere in comparison with all the other gases, those major gases like nitrogen gas, oxygen gas, and even carbon dioxide gas. Now, the sources of gases in the troposphere comes from four different sources. The first is the biogenic source, and then that means sources that comes from living things or living organisms, and then the trace gases could also come from the solid earth, and they could also come from the oceans, and they could also be formed in the atmosphere, or what we call the in situ formation source. Now we start out with the biogenic source. Well, the first source of gas is the photosynthesis process, where carbon dioxide would be combined with water in the presence of photons or energy or HF that comes from the sun to form CH2, or this is a simple monomer of a glucose or a simplified part of the glucose, and also would release the oxygen gas. And from here you can see that the carbon dioxide that comes from the air the photosynthesis process acts as a sink of the carbon dioxide gas, as well as some water vapor from the air, which would fix it into a solid, and at the same time it would release oxygen gas. Now, the decay of organic materials would also release tropospheric gas, in this case the methane, and this decay of organic material process constitute 80% of the amount of CH4 released into the atmosphere. And there are also microbe processes which converts nitrogen gas into ammonia, nitrous oxide, through nitrate respiration, and also nitrogen oxide. Then there's also the oceanic biological productivity releases, processes which release carbonyl sulfide or CS2, also some dimethyl sulfide, hydrogen sulfide, methyl chloride, and other. And then the fugitive emissions or incomplete combustion of hydrocarbon will also release a type of gas that contains organic carbons, or what we call the volatile organic carbons, which is a collection of organic carbon gases into the atmosphere. Aside from fugitive emission or incomplete combustion, or can be considered as anthropogenic releases or human-related releases, the plants also would emit some VOCs, and specifically the VOCs that are VOCs called isoprene, ethene, and monoterpenes. When we use some, when biological materials are used, they also emit some chemicals into the atmosphere, or those tropospheric gases, which includes carbon dioxide, carbon monoxide, nitrogen oxides, nitrous oxides, ammonia, sulfur dioxide, hydrogen chloride gases, hydrogen sulfide, dimethyl sulfide, COS, and CHCl3, and etc. Now, biomass burning is also a significant component of significant source of tropospheric gas, and biomass burning includes forest fires, either natural or agricultural related. Natural, such as forest fires, and agricultural related is through slash and burn activities of some crops, and this contributes to a large source of carbon dioxide, carbon monoxide, and so on, because of the combustion process that releases these gases. And then there's also photochemical reaction which produces ozone, and because the biomass burning produces some gases that promotes the ozone production. Although ozone is not directly released from the source or primary release of the source, it can get produced in the atmosphere through atmospheric reactions or atmospheric chemistry, and the components that contributes to this reaction comes from biomass burning activities. Now we go to the source of tropospheric gas. One of the source, which is from solid earth. Now, the solid earth source are like volcanoes, which are significant sources of atmospheric trace gases, and when it's erupts, it spews out ash, small particles, water vapor, carbon dioxide, sulfur dioxide, hydrogen sulfide, COS, hydrogen fluoride, and so on, the halogen compounds, HCl, HF, HBr, the methane, CH3Cl, hydrogen gas, carbon monoxide, and even heavy metals, for example, mercury, in a form of vapor that gets released from these volcanoes. Now, the emissions that come from these volcanoes are transported or ejected into the stratosphere, that means the layer above the troposphere, and this contributes to very long residence times of these gases because it has gone into the next layer of the atmosphere. Now, aside from volcanoes, the solid Earth also emits gases through noble gases, specifically the helium, argon, and radon, from radioactive decay process, such as the radioactive decay of uranium-238 and the radioactive decay of thorium-232. The amount of helium in the atmosphere is small because, well, if you remember the composition of helium in the air, it's relatively small compared to the rest. It's because it's relatively light, or because it is light, and then it constantly escapes the atmosphere, which causes the amount of helium in the air to be lower because it doesn't accumulate. And then there's the argon gas, which comes from potassium-40, or the radioactive decay of potassium-40, but it can accumulate in the atmosphere because of its relatively heavier nature compared to helium. And then there's the radon-222, which also comes from uranium, but it has a very short half-life of 3.8 days, which makes it not to accumulate in the atmosphere as long as argon. And that is reflected in the composition of these gases in the atmosphere that you saw earlier. Now, carbon dioxide is also released from the solid Earth, or absorbed into the solid Earth because of the sequestration processes that converts carbon dioxide in the air into carbonate rocks and marine sediments. But this process takes a very long time, very long period cycles as compared to biological processes such as photosynthesis. Now we go into oceanic sources of tropospheric gas. Now the oceans are large reservoirs of water-soluble gases. That means that if the gas is able to be dissolved into the oceans, then the ocean can act as this very large reservoir or this very large sink or source because of the massive scale of the presence of the water surface on Earth. Now, it can be a source of sulfur gases, and I did mention a bit about this in the earlier slides where we mentioned that gases can be released from the ocean in the form of carbonyl sulfide, dimethyl sulfide, or DMS, hydrogen sulfide, and so on. And these gases are a result of biological activities in the ocean. Now, the solubility of a gas in the ocean, in the form of a sink instead of a source, can be calculated or can be estimated using Henry's law. If you're interested to know about Henry's law, then you can take a look at the video that I provide earlier on this Henry's law. Now we go into in situ formation source, which means the chemical species is formed in the atmosphere through reactions in the atmosphere. Now there are two types of in situ formation. There's the formation reactions. There's the homogeneous reaction, where all of the reactants are in the same phase, specifically gas phase. And then there's the heterogeneous in situ formation reactions, where the reactants can be in two or more phases, gas and liquid. Now, trace gases emitted from the surface are usually in a reduced state, means at a low oxidation state. But when it gets into the atmosphere, it is oxidized in the atmosphere or goes to a higher oxidation state by these reactions. And then, aside from the four main sources described before, the biogenic solid Earth, the oceans and in situ formation, there's also a very significant component of anthropogenic sources or human-related sources. Because of the massive amounts of humans that are present on the surface of the Earth that are partaking in activities that releases gases. Now, because of this increasing population, anthropogenic emissions of trace gases have significantly increased, and these anthropogenic emissions are a major component of the budgets of trace gases. Even before, when the populations were low, it can be negligible, but due to the massive size of population, human population on Earth, it cannot be discounted anymore. Now, the extent of human influences on the atmosphere is one of the main themes of current research in atmospheric chemistry. The current state of the current research on the atmosphere is on the effects of human activities, specifically anthropogenic emissions, and how does this increased anthropogenic emissions and the amount of trace gas in the atmosphere would affect atmospheric chemistry or the composition of the atmosphere is the main theme of research now.